Well, without further ado, our last speaker before lunchtime is David Leal from Caesar Systems. David is going to be talking about four-dimensionalism in improving analysis of reference data. And so up to about 1:45, and then questions finishing for lunch at 12:55. So over to you, David.
Okay, thank you. So I will share my screen, hopefully. Share screen. Share from the beginning. Hello, is that okay? Can you see and hear me?
That's good to me, David. Thank you.
Okay, thank you. Well, other speakers have sort of touched briefly on how they got into this, and I think it's quite interesting because we all come through different routes, and it all sort of contributes to the scope of what's covered. I'm basically a stress engineer and writer of finite element analysis systems, all that finite element analysis systems. That was my day job. And then we started doing the long-term safety review for the AGRs in the CGB, and we could not access any of the data. Basically, we were back to paper, however much we had attempted to archive files and things. And so when we started work on Sizewell B, we thought we've got to do better. We've got to have some sort of way of holding our data in a standard format, which we have some chance of recovering 25 years in the future. And we kicked off a process through NAFEMS, which was then the National Agency for Finite Element Methods and Standards, now international. And we developed the finite element parts of ISO 10303 STEP. And that process is somewhat parallel to this discussion here. It's a way of tracking product design data and analysis data, and it's used a lot in the aerospace industry. So we got that out the door, and then it was a question of, well, yes, doing the shape of mechanical components and their stresses is one thing. What about the overall design of the plant? And we knew it was needed, and we knew we needed to keep track of what was in the plant, how the things fitted together, access to maintenance records, the big world out there, rather than just looking at individual components. And we didn't know how to do it. We were involved in ISO because we got the stress engineering out the door, and we went to speak to Matthew. And that's where a lot of this stuff kicked off. Matthew had an idea, and a lot of the stuff which rolled forward from that is stemmed from that. Indeed, I remember meeting Matthew in his office in the Shell Centre some decades ago, and a lot has followed from that. Matthew produced this stack. I'm somewhere up from the bottom. We're sort of working down in many ways. It becomes more technical as we go down. And at this middle layer, we've got the industry data models, a lot of models out there written in UML and Express, XML schema. A lot of them very ad hoc, not based on a foundation data model, which is the sort of problems which Matthew has addressed, which Chris will talk about the technologies for dealing with that. But one of the things is that these data models often had what people at the time referred to as magic strings. There would be a data model, and then what something was would be tacked on as an afterthought. It would be a data model for stress or just a shape model or a manufacturing model. And then the fact that it was a pump or a particular type of pump or a particular component within a pump would just be a string. And these were the magic strings. And the property, what the property was, there might be a model for a property, and lots of information about units of measure and how it was measured and accuracy. But then what is it? Is it the dimension of the shaft, the inside diameter, the outside diameter? And again, that was just a reference a magic string. Well, it gradually dawned on people that managing the magic strings was awful, and the concept of reference data was invented. It is data that other people define that I need to refer to. And as Ian said, a lot of this is classes, also this is types of things, types of properties, types of physical objects, types of activity. And the types, as I will get on to, go into more and more detail as you go up, essentially a stack of definitions. But it's not only types, there are individual things, individual, that you will have master, I mean, the synonym for reference data is master data. You will have particular places, particular organizations, particular systems, currency codes, country codes, all that sort of stuff. They're individual things, but they're data which other people have created and which there is an organization which has authority over them. So I'll go to the next slide. And really that we actually have a problem here, that there's a lot of interest, particularly, amongst the mathematicians and philosophers, that doing the foundation data model, this is good. There's a manageable community who are involved in both the top level ontologies and then the actual data models which start talking about things which exist in industry, activities, resources, the facilities, the connections between material things, the models which you deal with. And then there is the vast number of types of thing which are created in silos. And again, Ian mentioned that they often are unnecessarily created in silos, but there are an awful lot of them above. And they're often developed independently of any model, which is good in many ways, that they then become very agnostic. But sometimes they're often tied to a particular model and often are expressed using the terminology of a particular model. And some of these terminologies can be unfamiliar to engineers who are not experts in the model. That ISO 15926, which has been mentioned, talks about temporal parts. It talks about the thing called a functional physical object. Nobody in engineering, nobody in the colored bits above has any idea what that is. And so there is a sort of a task here to develop a layer of terminology which the domain experts working on the reference data items above can make use of. In some areas it's trivial. I mean, the people developing country codes presumably know what a country is, but if you're developing things in other specialized areas, it becomes far less obvious, and there is a core terminology is needed. And part of the problem is that these things have layers, and as you go up the stack, the amount of data you have to deal with increases, and the number of people. Let's talk through the layers in the stack. One of the big issues, in some ways the most difficult issue, is there are the generic classes from textbooks which nobody seems to own, and that is very often a really large problem. And it's certainly a problem, I mean, I'm involved with Matthew and Chris and others in ISO standards. Because nobody owns them, they're not defined anywhere in an authoritative source. And in some cases, there are incompatible authoritative sources, and you have to sort of get to grips with it all. I mean, recently I've been looking at in terms of the ontology for geometry and topology. What is the definition of a graph? There are many authoritative sources for definitions of what a graph is, and they are incompatible. So people further up the stack will be talking about graphs, but what definition are they using? And so there's a problem with the generic classes. Above that, we're getting standards, which is good. They're things you can refer to. Pipe threads, fasteners, etc. Types of nuts and bolts. That's good. They're there. Material types. This is good. The challenge there is that these things all exist on paper documents. And sometimes the paper documents specify the magic strings that refer to them. You know, you shall use this particular text string to refer to this particular material grade. It would be far nicer if this could be turned into linked data. These objects had URIs. Units of measure is a particular area of problem. Again, that, you know, there's the BIPM and ISO 80,000 sits on top of units of measure, but they have made no attempt to make these computer referenceable, and therefore there are different organizations like NASA have set up ontologies covering this. But again, it's a question of where the authority lies. And the authority actually lies with the BIPM. It would be good if they stepped up to the plate and published it in a way that we could reference their stuff. As you go up the stack again, things are expanding out. There are NATO, there's the NATO codification system. It's got 7 million items. It's got about 5 or 6 million items. Other organizations have these things. And then as you go up again, there are manufacturers' catalogs. And there are the links all the way down the stack. If a manufacturer is making a particular type of item, they will be specifying its properties, its material grades, using the terminology defined lower down the stack. And they may well specify that it complies with a particular commodity item, i.e. we supply this commodity, which complies with this NATO commodity code. So the links are up and down the stack, but the numbers of items goes from the thousands at the bottom. The process industry, the ISO 15926 core terminology was initially about 12,000 classes and is now going to be expanded out to about 30 in the next release. But as you go up the top, there are millions of items, and we essentially have to use these, just out of sight on this pyramid are our data models, and we have to make use of all this, and we have to be able to use reference from our data models all the types of things defined in these particular layers. The other thing, the problem, is that we don't specify what the bottom is. Within here, we're going for this 4D analysis, and it is especially powerful for sorting out the terminology. But we can't impose it on everybody, and there are legacy data models which are out there. The approach which we're trying within ISO, and I think it's several of the team on the National Digital Twin are involved in this, is to define essentially a core terminology which the people working above are going to be able to relate to. They will not necessarily understand the terminologies used down below in the different foundation data models, but the core terminology, the idea is it should be understood by engineers. And we're trying to make sure that it is agnostic as to what is below, in that the people developing the core terminology do have 3D data modelers, particularly people concerned with the NIST Industrial Ontology Foundry, which is essentially a set of 3D data models based on the 3D upper ontology called the basic BFO, Basic Foundation Ontology. So we've tried to be agnostic. And then above this, we are encouraging people to use the terminology of the boundary layer, so neutral set of terms. Because as I said, the problem is that at the bottom, the terms are very specific, that there are terms for even simple things, even something as sort of fundamental as a mechanical assembly. There are terms such as occurrences. And as I said, the ISO 15926 has functional physical object. And sometimes the people in a silo will be linked to a particular data model and will use that terminology in preference for many others. And our objective is gradually, if we can establish a neutral terminology which fits onto, which anybody working in terms of creating a data model can say, well, this term fits to this object in our data model. In fact, of course, we're using the 4D to validate this, and a lot of the understanding comes from 4D, but when we actually go out there, we have to sell it to people who are not necessarily wedded to 4D. Within ISO, we sort of looked at it and thought, right, well, we need to start with a something analogous to a doubling core, a core set of terminology, and so that these things will be understood by the people working in their silos above, and will be easy to map to the ontologies below, and will have precise mappings, and not the same mapping to every ontology, a very particular mapping to the 4D ontology, and a lot of the thinking behind this has been driven by the 4D view. And hopefully all these terms are sort of recognizable. I noticed there's position in organization, which came on Matthew's early slide. It is not the same as a person. And it's a sort of role. We also have things like assembly elements, which I'm going to get onto in a minute. This term is something we've defined. Again, assembly breakdowns are defined. What these things are then map to the 4D ontology. But we hope to isolate the domain engineers as much as possible from dealing with the precise terms in the 4D ontologies. So the work has started by just words, and we've sort of tried to mine definitions from other places. There's the well-established standard for system engineering. It's fine. Every word there in black is in bold is a defined term, and hopefully will have a place in the ontology. So we about systems are divided into system elements, and what's going to come up in a minute is, of course, what is the relationship between a system element and an actual material object? It's quite complicated, but what is written here is reasonably understandable and usable by the people above doing the domain work and the people below working on the ontologies. So the other thing we're doing is looking at examples, and the examples on this slide, I'm going to show a number of examples, which were examples which came out of the work which we did on 15926 and the reference data. And curiously enough, the same examples crop up because they're sufficiently simple for everybody to understand. And this example, although it comes from the 15926 world, is also the example which they use in the QIF standard, the quality information standard for metrology of design data. They're talking about metrology for assemblies, therefore they need an example to establish the terminology. And this is the example. And I trust it's sort of reasonable. Everybody understands what they are. It's terminology in there. Certainly it shows to a certain extent the layers. We've got the generic classes, the textbook stuff, which, as I said, is often a problem about who owns these classes. But then you get to manufacturers' classes where it is obvious who is the source. And of course, as soon as you, and just going back to reference data and its use, as soon as you're doing maintenance records, the design information is your reference data. For the point of view of the designer, or it's their actual data, the data they're using and creating. But for the purpose of somebody doing the maintenance, it's somebody else's data. It is the data you refer to and leave alone. And we assign some terms we cast about. And one of the things is that we've got assemblies and systems. A motor car is both an assembly and a system. Most things are both assemblies and systems. It's just a choice of view. We've got generic kinds and we've got specific kinds. And there's a distinction here quite clear that we understand. There's a difference between the near side front wheel and a motor car wheel. And I've got two concepts here related to motor car wheel. It's types of wheel and where a wheel is used. And so that's fine. Here it is obvious. I'm taking a simple example to make it completely obvious. It becomes less obvious in more difficult circumstances. So we can sort of do something like this. We know that there's a stack of hierarchy of classes for the motor car, and then for the wheel, yeah, some wheels are near side front wheels, some wheels are Opel type A wheels, we can do this naively, basically just based on language, and the layer at the top is our the core terminology. But of course, there's a lot missed if you just do this. We're talking about how you get good reference data. There's a lot missed. It's been we've touched on before. In fact, I'm really just going into more detail of what Matthew, Ian, and Al have already said. There's a problem here that there are things that we know that the type of a wheel remains constant throughout its life. We may actually look at the material and say, actually, the material existed before it was a wheel and will continue to exist after, and being a wheel of that type is just a state of the material. That is fine. But during that state, the fact that it remains a type A wheel wherever it is installed, the near side front wheel has to be part of a motor car. It can't be a near side front wheel in the abstract somewhere else. It can't be a near side front wheel when it's in the store. So these are obvious things. And the reference data needs to reflect this, and so that we don't argue about how exactly we structure these classes. And we get back to these diagrams, and these diagrams are absolutely fundamental for organizing the reference data. And the arguments have, in terms of creating reference data, often go round and round in circles. And even taking this very, very simple diagram, it's quite instructive. First of all, that the near side one wheel, being for an opal, actually has properties. That is a class which has an allowed ranges of tire pressures. So it's something which is a very physical thing. And also, if we're creating maintenance records, we would send somebody out to check the tire pressures and tread depths and report it. Near side front wheel of this car has these properties. So the near side front wheel boasts the class of being an Opel Vectra near side front wheel has properties. It's allowed ranges of pressures, and only some wheel types are allowed there. So it's a physical thing. And when we get an individual, we can measure its properties. So there's no doubt that this concept in the red, within the red arrow, is a real physical thing, because we can measure it. We can go and kick it. But it isn't there all the time. And again, it's what Matthew said, it's a real philosophical thing. Sometimes it isn't there. When you're making the records, you might well say missing if you actually went to the vehicle and the wheel wasn't there at the time. So it's something which requires a certain amount of thought in terms of noting that a type of wheel, in terms of how it's manufactured, is different to a type of wheel installation. And so we can go down and start doing the previous diagram a little bit better. And so what we have is that we got the vehicle, which exists through all of its life, and through all of its life, it has a near side front wheel. This is something which is necessarily a part of the vehicle. This near side front wheel at some time has a state, and at that state, it is also a state of a particular wheel. So that if it has a puncture, it is both the near side front wheel and that particular wheel that has a puncture. And this was the argument which Matthew talked about at his opening slide, to do with the President of the United States. And it's sort of fundamental, and it crops up in engineering all the time. And we then go up a level and say, right, we can certainly start classifying these things. And we're classifying it into things which are essentially manufacturer defined, so that we can look at the near side front wheel, and we can say it is an Opel Vectra near side front wheel, so we know what tire pressures it ought to have and what type of wheel it is. And looking up again, we're looking at, okay, going into the textbook stuff, yep, these are wheels. And we now have this terminology which links it into the top level ontologies. Assembly elements are defined with respect to the assembly, their identity basis. And again, it's a key term which Matthew used. The identity basis relies upon the assembly of which it is a part. Whereas the identity basis for a particular wheel, well, it has, it'll have a serial. It might have a serial number stamped on it. The identity basis is the material. So the use of this 4D diagram will be implemented very naturally in any of the ontologies we're considering. Borough 15926, IES, it's fine. The terminology which I've used here, assembly element and component, we've defined the words, and we know very precisely how those words relate to the 4D ontologies. but also they map into existing legacy data, and legacy data models such as ISO 10303-242, which is the automotive and aerospace design. They use different words, but these words can be mapped in, and the same for QIF. Again, we can use yet another terminology in which we can relate to. And so, yes, so the final one here is linking in, and those particular objects exist within ISO 15926. Just a sort of side thing, you know, motor cars, do they always have material continuity? Well, no. We can refer to the motor car as the Prime Minister's car. It's certainly a car. Is it the same car all the time? No. And here, I mean, again, there's a distinction between systems and assemblies. The Prime Minister's car is not an assembly element. It's a part of a system. It doesn't actually fit to anything else. The terminology system and system element is well established in system engineering. They're more 4D minded people. And whereas assembly and assembly element is not. Assembly element, they think of as part occurrence. Sometimes it's just replaceable part, but we need to establish the terminology and then fit it into the 4D world. And by establishing the terminology, we're going out, we're relating to other people's information reference data. You know, we can't, they're probably not very interested in the details of a top-level ontology or 4D, but they're happy to embrace a understandable language for what they do. Having said all this, there are times when actually being a particular material continuity is really, really special. So it doesn't matter to very much most of the time which wheel is actually the near side, front near side wheel. And we have a term, the term wheel is quite sort of vague in that sense that I put, I gave it two subclasses. Some objects are very specifically tied to the whole life of the thing. A material test specimen, it has to have material continuity. You do not want to swap it around for another one. Otherwise, everything falls in a heap. The organizing the reference data and organizing the terminology has to make the distinction between the specimen's role and the actual specimen, which begins when it is cut from the sample and ends when it's broken or finished from the test. The same thing applies to batches of material. Again, you don't want the batch of material documentation to be separated from it by another batch that has the same role. And same is true with people, that there is a person and there is a person role in an organization. There are some properties that will be common to both, but it needs to be very carefully separated. And also it's a thing which affects terminology. We don't, when we say person, we do mean a particular person with a birth and a death and a blood group and all that sort of thing, not a person role. So organizing the data in the reference data to make these things clear is actually quite important. I've got another sort of coming towards the end now and going through the arguments which led to a lot of the initial work on organizing the reference data and sorting out how reference data fitted to 4D was the anchor and the pump. It's a bit of a fun one, but it's these slightly silly things which often validate your reference data. What is an anchor? Is it something which has the form of an anchor, or is it something which is actually used as an anchor? And the criterion for being used as an anchor is it's got to be heavy, and it mustn't float, and it's got to be able to attach a chain to it. But other than that, there's nothing specific about the form which is absolutely essential. So again, we have this. We have an anchor lost. We have a spare bit, a spare object then becomes the anchor. That is fine. We have two objects. There's the Medway Queen anchor and the Medway Queen anchor as a role in terms of how the ship is moored up. And then we have a physical object, which is not intended to be an anchor at all, but actually has that role after a particular point in time. It's slightly silly, in fact, quite realistic, but it does illustrate the difference here. And so actually, in this case, there isn't a very natural superclass between anchors, as in the role they play, and the anchors and the things which have the form of an anchor. Anything will do. And so we have this sort of example here where, you know, the criteria, it's got to be heavy and it's fine. The role, underneath the anchor, the textbook concepts of anchor, there's a very specific class here, which will be an approved anchor role. The authority for that will be the Maritime and Coast Guard Agency. They will specify the criteria that they must have. That class is defined by them. Davy & Co that make anchors, they will define the class underneath the form of their article number. And Davy & Co might assert that a temporal part, a state of one of their anchors used for mooring a 50-ton ship is something that will be approved by the Maritime and Coast Guard Agency, and it's this subclass in the bottom, and hopefully the use of the anchor in 2020 was in fact an approved use.
Sorry to interrupt, David. We need to finish in 5 minutes. So
that's last. I'm terribly afraid it's the last slide. Fortunately, right. So my point is that that the space-time diagrams, the 4D view of the world is a key tool, and it stops arguments going round and round in circles. And my second point is that the way we use this tool is making the engineering terminology precise at the interface between the top level ontologies and the vast world of reference data which sits above them. Sorry for going on too long.
Thank you, David. As I say, we break for lunch at 5 to 1, and we come back with our session 2 at 1:45. So I can't see if there are any new questions in chat. Does anyone have any questions they'd like to quickly post? Not seeing anything coming up. Obviously, if anyone thinks of something during the lunch break, they can still post it retrospectively. I'm sure David would be happy to have a look at that. Okay. Anyone for anyone? If not, we can break for lunch, I guess.